Okay, I am saying hello from West Virginia, and I am not, but that's okay because I have joke of the day and I know you're ready for it. So what is blue and smells like red paint? Blue paint. Oh dear. Okay, let's take a look at the product rule for radicals. The product rule is a super helpful rule, as well as the quotient rule, which will be in the next video. So let's take a look first at these couple of examples. Now we saw these in the previous video, and they were to illustrate to us that the order in which we do the operations is very important. Because in the first example, we need to add the two numbers first and then take the square root, as opposed to the second example, which says, let's take the square root first and then add them. And remember, we came up with entirely different results based on the order in which we did it. So when we added first, we got square root of 100, which gave us 10. And in the second example, where we took the square root first, we got 6 plus 8, which gave us 14. And that showed us that no, I am not going to get the same result when those operations are set up differently. Notice, however, in this case, what we have here is, first we're going to multiply 4 times 9 and get 36. And then the square root of 36 is 6. Notice I'm talking principal square root here. Technically, there are two numbers that I can multiply together to get a 36. That would be a positive 6 and a negative 6. But this is principal square root. Same thing happening up here. I'm dealing with principal square root. This one says I'm going to take the square root of 4 first, which is a 2. I'm going to take the square root of 9 next, which is a 3. I'm going to multiply the two together, which gives me a 6. Oh my goodness, I got the same thing. This is an illustration of what we call the product rule for square roots. The product rule says, okay, for two numbers that are greater than or equal to 0, two numbers greater than or equal to 0, in other words, they cannot be negative numbers, and it's okay for them to be 0, and they are real numbers. This is the symbol for real numbers. So I need two numbers underneath this radical. They cannot be negative. They're going to be real numbers, which means I can have fractions. I can have decimals. That's okay. But I cannot have negative numbers, and I cannot have complex numbers, which is we'll talk about that much later. So in other words, here's what happens. I can either go ahead and multiply them first and take the square root, or I can take the square root of each number and then multiply it together. I'm going to get the same result either way. That's what this says. Remember the pan balance idea, that when you have an equation, it means what's on this side and what's on this side are all balanced out. They have the same value. So if that's the case, that means this is the same as this. So if I multiply them together and then take the square root, as I did here, or if I take the square root of each number and then multiply the results together, I'm going to get the same thing. That's what your product rule for square roots says. This is so helpful for simplifying your radicals. And a lot of people will say, I thought I was done simplifying my radical, but then I was told I needed to go further, and I never know when I can stop. Folks, ta-da! Here it is. This is how you're going to know that you are done simplifying your radicals, right here. A square root is simplified when there are no perfect squares underneath the radical. Now, a perfect square is a number that you can take the square root of it. So in other words, a 9 is a perfect square, because what's the square root of 9? 3. A 4 is a perfect square, because what's the square root of 4? 2. A 36, what's its square root? 6. 64, what's its square root? 8. These are all perfect squares because I can take the square root of them. What about a 7? Can you think of a number that you can multiply by itself to create a 7? Nope. So 7 is not a perfect square. Same thing with, say, for instance, an 11. Can you think of a number that you can multiply by itself to create an 11? No. Now you may be thinking, okay, you're talking about odd numbers. Well, let's talk about this, a 10. Can you think of a number that you can multiply by itself to create a 10? No. A 10 is a 5 times a 2, but there's no number that I can multiply by itself to create a 10. So 10 is not a perfect square. Perfect squares are numbers that you can take the square root of. You know you're done simplifying your radical when you have no perfect squares underneath that radical. In addition, if you have no pairs underneath the radical. Now that's a very strange concept, and I'll explain that a little bit better through the examples that I've got. So let's take a look at these examples of simplifying our radicals. Now, here I have the square root of 150. So what I want to do in order to simplify that radical is I want to ensure that I have no perfect squares underneath it and I have no pairs underneath it. Now first I'm going to look at that and I'm going to say, can I think of a number that I can multiply by itself to create a 150? Nope, I can't think of anything. So now what I'm going to do is I'm going to say, well, let's simplify that radical. And I'm going to utilize that product rule. The product rule says I'm going to find two numbers that I can multiply together, and I'm going to try to take the square root of each of them. So what I'm going to do here is I'm going to break down, break down, break down, break down. I grew up in the 80s and we were break dancing, so break down, break down. So I'm going to break down that 150. 150 in my eyes is going to be a 15 times a 10. Now other people will think of other numbers, and I'll illustrate that in a minute, but I've got 15 times 10. So now my product rule says I can separate that out and I can call it square root of 15 times square root of 10. Now, can you think of a number that you can multiply by itself to create a 15? Nope. Can you think of a number that you can multiply by itself? We already talked about that. There's nothing I can multiply by itself to create a 10. So I'm going to once again break down, break down, break down. So 15 is 5 times 3, or 3 times 5, either way, and 10 is 2 times 5. And so now my product rule says, okay, I can separate this out. And I can do square root of 5 times square root of 3 times square root of 2 times square root of 5. Now, can you think of a number that you can multiply by itself to create a 5? No. Can you think of a number you can multiply by itself to create a 3? No. 2? No. And we've already established not for a 5. Now, can I break those numbers down? Break down, break down, break down. No, 5 is 1 times 5. And that's not going to help at all. 3 is 3 times 1. 2 is 2 times 1. So in other words, if you cannot break it down into something other than 1 in itself, if you can break it down into something other than 1 in itself, keep going with that. But when you are stuck into just 1 in itself, you're stuck. 1 in itself, I'm stuck. 1 in itself, I'm stuck. However, this square root of 5 represents some crazy decimal number. It represents a number. So I've got a number here, a number here, a number here, and a number here. All these numbers are being multiplied together. Now you know that multiplication is commutative and associative, which means you can switch the order of multiplication. I can switch the order all I want. So in other words, it is possible to put the square root of 5s together like this, and then put that square root of 3 and that square root of 2 back here. Totally legal because multiplication is commutative and associative. The reason I did that is because now here, those square root of 5s, I'm going to use my product rule, but I'm going to use my product rule backwards. And I'm going to put them together as 5 times 5. Because 5 times 5 is 25. And now, can you think of a number that you can multiply by itself to create a 25? Yeah, it was right there, 5 times 5. So the square root of 25 is just a 5, and now it's 5 times the square root of 3 times the square root of 2. Now, I cannot think of a number I can multiply by itself to create a 3, nor for a 2, and I can't separate those out. It's not going to do me any good, but I can put them back together underneath one big radical utilizing that product rule backwards. So what I'm going to do then is I'm going to put them together as 3 times 2, giving me 5 square root of 6. And that is simplified because, remember, I didn't want to have any perfect squares underneath the radical. 6 is not a perfect square. A 6 only breaks up as a 3 times a 2. That doesn't help at all. And I don't have any pairs underneath the radical because when I was back here, there were no pairs. Now let's step back a second. I know a lot of you are going, oh my gosh, that is so much to do. There are a ton of shortcuts that you can take in this. I wrote out every single step so that you'd understand why you're allowed to take the shortcuts that you're allowed to take. So let me calm you down here and show you those shortcuts. First off, right here, remember I said no perfect squares or pairs? There's a pair right here. When you see a pair, what you can do is you can take one out and it dissolves the other. It doesn't really dissolve it. It's not magic, it's math. But what happens here is when you take the 5 out, as you see right here, notice that this one's no longer there, and I have that 3 times 2 right here. So what happens is when you see a pair, you can take one out, it dissolves the other, only because that pair creates a perfect square. And the square root of that perfect square is the number that would, the one of those pair. So when you see a pair, take one out, dissolve the other one. That's a shortcut that you can take. And if you would have done that right here, you could have skipped this step and this step. Now, another shortcut that you can take is right up here, I didn't necessarily need to separate them out. I could have looked at this and I could have said, do I know the square root of 15? No. Do I know the square root of 10? No, because I can't think of a number that I can multiply by itself to create a 15. I can't think of a number that I can multiply by itself to create a 10. So rather than separating them out this way and then continuing on, I could have just said, I'm going to keep one big radical like this, and I'm going to say 15 is 5 times 3, and 10 is 2 times 5. And right there, I could have very quickly and easily said, oh, I see a pair. I see a pair of 5s. And when I see a pair, I'm going to take one out and dissolve the other one. So I would take that 5 out, dissolve the other one, leaving me with a 3 and a 2 underneath. Notice that would take me right there. And I could have skipped every bit of this. That's a lot that you can skip. And that's good. I want to be able to skip all that. But it was very important that you saw all these steps so that you would understand why you're allowed to take the shortcut that you're allowed to take. It has everything to do with that product rule. The product rule is just the greatest rule ever. So now I want to illustrate, what if you didn't think of 15 times 10? What if you were one who said, I thought of 75 times 3? No, sorry, 75 times 2. I apologize, 75 times 2. What if you said, I thought of that? Well, that's okay. Can you think of a number that you can multiply by itself to create a 75? No. So you're going to continue to break it down, break it down, break it down, looking for those perfect squares and pairs. So then you could say, well, 75 is going to be 3 times 25. Now, do you know the square root of 25? Yes, it's 5. So when you see one that you know the square root of, you're just going to take its square root out. And when you take the square root of 25 out as a 5, you'll be left with this right here again. 5 times 5 on the outside, 3 times 2 underneath, leading you to that correct answer of 5 times square root of 6. Now, what if you were one who said, I wouldn't have thought of either of those? I thought of 50 times 3. Sure, no problem. Can you think of a number that you can multiply by itself to create 50? No. How about 3? No. But you do know that 50 is 2 times 25. And look, there it is again. So I know that the square root of 25 is 5. I'm going to take that out. And that will leave me with, aha, there it is again, 3 and 2 underneath, 5 on the outside. So see, it's okay if you don't think of the number combinations that I think of, or you don't think of the number combinations that your friend thinks of. The main goal is break down, break down, break down, and look for perfect squares or pairs. If you see a perfect square like you saw right here, take the square root out. If you see a pair like you see right here, take out one, dissolve the other, because these two together will make that perfect square. Now, let's continue on. Here, notice I've got square root of 11 n squared. So like I said up here, I could separate them out into their individual pieces, or I could leave them together just looking for perfect squares and pairs underneath the radical. Now, do you know the square root of 11? Can you think of a number that you can multiply by itself to create an 11? Nope, I can't either. Now, how about breaking up the 11? You're right, it's only 1 times 11. And remember, that's not helpful at all. at all. So I'm stuck with this 11 underneath. I can't break it up into anything useful. I'm stuck there. However, take a look at this n squared right here. Can you think of what you would multiply by itself to create an n squared? Yeah, n. N times n is n squared. So this will even work with variables. So I'm going to pull the square root of that n squared out as an n, leaving the 11 underneath. There we go, it's simplified. Because I no longer have perfect squares underneath the radical, and I don't have any pairs underneath the radical. All right, so let's take a look at another one. Wow, crazy stuff happening here. And there's a couple of ways of handling it. Notice that they are separated. I can put them together underneath one big radical, and then I can go with that. Or I can go ahead and break this one down, putting them together. Whatever way you want to do it. The whole goal is make sure you don't have perfect squares and pairs underneath that radical. And then when you've completed all that, put it together. So what I like to do is I like to go ahead and put them together underneath one big radical like this. And then I like to go ahead and start breaking it down, looking for those perfect squares and pairs. Can you think of a number that you can multiply by itself to create an 8? Nope, I can't either. But I do know that 8 is 4 times 2. So I'm going to break that 8 up as 4 times 2. Now that x squared, can you think of what you can multiply by itself to create an x squared? Yes, an x. So I'm going to leave that one as it is because I'm going to pull the square root of that x squared out. Now, that 6, can you think of a number you can multiply by itself to create a 6? Nope. Now, that 6 breaks up as 2 times 3, which will be useful here in a minute. And I can't think of anything that I can multiply by itself to create that x. Now, let's step back a second. That 4 right here, can you think of a number you can multiply by itself to create a 4? Aha, a 2. So, I'm going to take the square root of the 4 out. And I'm also going to take the square root of the x squared out. So I have a 2 and an x sitting on the outside. Underneath, I've got 2 times 2 times 3 times x. So 2 times 2 times 3 times x. And remember, not only am I looking for perfect squares, I'm also looking for pairs. Do you see any pairs underneath? Aha, a pair of 2s. I feel like I'm playing poker now. So, with that pair of 2s, remember 2 times 2 will give me a 4. We've already said the square root of 4 is 2. So that square root of 4 will come out. And remember, when you have a pair, you're going to take one out and dissolve the other one. So this 2 will come out. Now the question is, when it comes out here, how does it combine with that 2? Am I going to add them together? Am I going to subtract them, multiply them, divide them? What am I going to do? Notice that this is one great, big, huge what type of problem? Yes, great big huge multiplication problem. 8 times x squared, 6 times x. These are sitting right beside each other, and sitting up against means what? Multiplication. So this is one great big huge multiplication problem. So when I take the 2 out of here, I'm going to combine it with this 2 by multiplication, and I'm only left with a 3 and an x underneath. So 2 times 2 will give me 4, and I'm left with an x. And I've got my 3 and my x underneath. Ta-da! There it is. Okay, let's try one more. Once again, looking for perfect squares and pairs, can you think of a number that you can multiply by itself to create a 45? I can't either. How about the x? Nope. How about the 3? Nope. So again, what I like to do is I like to go ahead and put them together underneath one big radical and then start splitting things up, looking for perfect squares and pairs. Now that 45, I do know that it is 9 times 5. You may have thought of 3 and 15. That's perfectly fine. Perfect squares and pairs. Look for perfect squares and pairs. So 45 is 9 times 5. And again, looking for perfect squares and pairs. Do you know the square root of 9? Sure do, because 3 times 3 will give me a 9, so I'm going to take its square root out. And do you see anything else in there? Aha, I see a pair. So there's a pair of x's right here. And remember, when there's a pair, you're going to take one out, dissolve the other one. So what comes out is square root of 9 is 3. The x will come out. I'm left with a 5 and a 3 underneath. There's nothing more that I could do with those. I don't know the square root of 5. I don't know the square root of 3. I can't break them up into anything useful because it becomes a 5 times 1 and a 3 times 1. So I'm going to multiply them back together, giving me a 15. So I have 3x square root of 15. Ta-da! It is simplified because I don't have any perfect squares or pairs underneath the radical. So I hope that helps you with, number one, simplifying radicals, and number two, with the product rule for radicals, because that product rule is so helpful for simplifying your radicals. I hope it helps. Have a great day.